So first of all, I decided to change a little bit the title of my talk and make it more general. So it will be about synthetic gauge fields, not in just one-dimensional, but in one-dimensional and two-dimensional. The reason is that after this, this work was submitted to the conference, we did very nice work together with my PhD student Valery Kozin and SHELYKH Ivan about excitonic analog of anomalous Hall effect, which also has something to do with synthetic gauge fields, as I'm going to show you. And I decided to include this part also in this presentation. So as I am speaking in the section Polaritonics in Clermont-Ferrand, I think it's very nice to say that the people who contributed, among the people who contributed to the topic which I'm going to discuss today, three, myself, Anton Nalitov, and SHELYKH Ivan, are directly connected with Clermont. So I think that my talk perfectly fits this polaritons in Clermont session. So I don't know, I'm again frozen. Maybe I have the same problem as SHELYKH. Yeah, now it should be okay. Here is the outline of my talk. I will first discuss a little bit the general concept of the gauge fields. Then I will say a couple of words about already existing proposals of introduction of the gauge fields for excitons and polaritons. And then I will go to the original part of my talk. I will speak about the possibility to create an analog of Rashba splitting in 1D asymmetric polariton waveguides. And finally, I will say a couple of words about our new work related to anomalous Hall effect for excitons. So how gauge fields appear in physics? Gauge fields appear from symmetry consideration, and the basics of the introduction of the gauge field is as following. So imagine that we have some quantum system, and imagine that this quantum system has some n internal degrees of freedom. It can be spin, for example, it can be flavor, or any other internal degree of freedom as you wish. So then we have, in the one particle approximation, we will have the Hamiltonian, which can be represented as a sum of the kinetic energy term and the potential energy term. Then we can construct the Hamiltonian density, just calculating psi cross h psi. And then we can note that if you make a global transformation of this type, global means that we multiply the wave function by omega, and omega can be here as just a phase factor or n by n unitary matrix. Then the Hamiltonian density will not change. But on the other hand, if you do the same type of the transformation, but make it local, local means that omega will now depend on the coordinates. Then Hamiltonian density under this local transformation, known as local gauge transformation, will change because kinetic energy term contains the operator of the differentiation, and this operator of the differentiation will not commute with omega if omega is R-dependent. However, if we make a canonical substitution, introducing here A, where A is known as some effective gauge potential, and if we demand that A transforms under the following rule, when we do the following transformation with the wave function, we can immediately see that the Hamiltonian density will be invariant. So as I mentioned already, if we consider psi in the form of this n-dimensional spinor, then there are two types of the possible gauge transformation. One first possible type of the gauge transformation is just multiplication of the wave function by a phase factor. So this is corresponding to so-called abelian fields. Why they are called abelian? Because in this situation, the components of the effective vector potential will be just normal functions. So they will transform under standard gradient transformation if they are just normal functions. Of course, different components of the vector potential, they commute with each other. And well, we can introduce something which looks like magnetic field, known as effective magnetic field, just as a curl of the vector potential A. On the other hand, if we do SUN gauge transformation, then the components of the gauge potential should be n by n matrices. They are not necessarily commuting with each other, so this is corresponding to the so-called non-abelian gauge field. In this situation, when we introduce the analog of the tensor of electromagnetic field, it will contain some additional term given by the commutator of the matrices corresponding to the different components of the gauge fields. And well, then the analog of magnetic field will be also written in terms of the matrices. So how all this works in the domain of condensed matter, and in particular in the domain of polaritonics. So I want to compare here two situations, one situation corresponding to two-dimensional electrons, and another one corresponding to two-dimensional polaritons. So for two-dimensional electrons, it is pretty easy to introduce both abelian gauge field, and in the case of the two-dimensional electrons, abelian gauge field will be just corresponding to the external magnetic field. Electrons have electric charge and they are coupled to the magnetic field. And as for non-abelian gauge field, it can be represented by spin-orbit interaction of either Rashba or Dresselhaus type. So here I consider the example of the Rashba spin-orbit interaction. For Dresselhaus case, everything will be pretty much similar. So this is Rashba Hamiltonian, and simple algebra gives you that this Rashba Hamiltonian can be rewritten in this form, which exactly coincides with what we have here. So here we have the canonical substitution, but now, as you can see, the components of this gauge field are matrices proportional to the Pauli matrices. So what about polaritons? For polaritons, if we just consider one two-dimensional case, there is no possibility to introduce U1 gauge field, so magnetic field will not play this role because the charge of the polaritons and the charge of the excitons is zero. So what about SU2 gauge fields? So polaritons have TTM splitting, and it is generally said that TTM splitting for polaritons represent an analog of spin-orbit interaction for electrons. This is not fully true, and the reason is different symmetry of the effective magnetic field created by Rashba-Dresselhaus spin-orbit interaction and effective magnetic field created by TTM splitting. So if you write a Hamiltonian corresponding to the TTM splitting, so TTM splitting will give us non-diagonal terms, you will see that differently from Rashba and Dresselhaus spin-orbit interaction for electrons, we will have the square here, which actually means that if you write everything in terms of the Pauli matrices as it is done here, there is no possibility to represent this part of the Hamiltonian in terms of the canonical substitution. So here, just a reminder why it is like that. So if you have effective magnetic field, if you have an effective magnetic field for corresponding to Rashba spin-orbit interaction given here by black arrows, it will make one round trip, one turn when you make a round trip around zero in the reciprocal space. And if you have effective magnetic field given by TTM interaction, it will rotate twice, as shown here by red arrows. Or in terms of dispersion, if you account for Rashba-Dresselhaus spin-orbit interaction, you will have for electrons the formation of the Dirac cone here at k equal to 0. And as for polaritons, you will have just two touching parabolic dispersions, which should rather be described in terms of the different effective masses of longitudinal and transverse polaritons and not the gauge field. So to have gauge field for polaritons, we somehow need to move out from purely symmetric two-dimensional case. And there are already proposals how this can be done. So the first one was done by myself in collaboration with Guillaume and Dima Solnishkov many years ago. So this was corresponding to the polaritonic ring placed in the external magnetic field. This external magnetic field will induce Zeeman splitting, and together with the effect of the TTM splitting this Zeeman splitting will induce Berry phase for polaritons moving clockwise and anti-clockwise in this ring. So this Berry phase will be different from for polaritons moving in opposite directions, which after some algebra will give you exactly the Hamiltonian in terms of the canonical substitution with effective vector potential depending on the amplitude of the Zeeman splitting and longitudinal transverse splitting. There was also proposal coming from Anton Nalitov and Guillaume and Dima Solnyshkov that in the case of polaritonic graphene, when you move from purely two-dimensional case to the patterned microcavity with hexagonal symmetry, so in this case, you will see the dispersion form of the Dirac cones around K and K prime points. And they have shown that in this situation around Dirac points, you will have the Hamiltonian, which can also be considered in terms of the effective gauge field, which has SU2 symmetry and which looks pretty much similar as Driscoll's spin-orbit interaction for 2D electrons with AX and Y given by these expressions. Today, I would like to mention two other possibilities of the introduction of the effective gauge fields. So first example will be corresponding to one-dimensional polariton system, and second example will be corresponding to the two-dimensional, not necessarily even polariton system, but two-dimensional exciton system. So let me start from one-dimensional system. So the geometry which I am going to consider is shown here. So we have one-dimensional polariton waveguide. Polaritons are moving along x-axis. They are confined along y-axis, and the nature of the confinement along y-axis is asymmetric. So this asymmetry is important, and this asymmetry, as I will show, is responsible for the effect that I am going to demonstrate. How you can organize this asymmetry? For example, you can cover half of the waveguide by a metallic plate, which will change the structure of the photonic modes, and as a result, the profiles of the confined modes, in particular the profile of the ground state, and I will focus on the ground state, will be highly asymmetric. In this situation, I can write the total Hamiltonian of the system as the sum of the H0, which is spin independent, and it is given here. So this is just propagation along x-axis plus confinement along y-axis, and V. And V is given by TTM splitting in this polaritonic system. So you see that it is quadratic in K. So itself, it cannot be treated as effective spin-orbit interaction, and there is no way to treat it directly as some gauge field. However, if you project everything on the ground state, this gauge field will evidently appear. So what is the procedure? So I would like to use the perturbation theory, and I would like to represent, to project everything on the ground state and to represent the Hamiltonian projected on the ground state as some of the terms corresponding to the perturbation series. So here I give you the expression for the first two terms. So first I solve the problem with Hamiltonian H0. It corresponds to the propagation along x-axis, confinement along y-axis, and the presence of spin or polarization of the polaritons. So, and then, as I said, I write the Hamiltonian as sum of the three terms. I will go up to the second order perturbation theory, and then I just use the standard expressions from quantum mechanics for H0, H1, and H2. So H0, it is just the Hamiltonian of the ground mode without any account of the TTM interaction. H1 is just the matrix element of the V taken for the zero of the wave function. So H1 will look like that. So here H1 again will not give us any terms which are linear in K. It will contain just just a constant term, which is nothing but the mean value of y of the ky along the ky squared along the direction of motion along which the motion is confined, and you have the standard kx squared term, which is coming from this the square of this term here. So the interesting thing here, banal but quite strangely not mentioned by anybody before, is that differently from the case of the two-dimensional polaritons, the dependence of the TTM splitting in one-dimensional waveguide, the dependence of the absolute value of the TTM splitting in one-dimensional waveguide on the kx is non-monotonous. So you see that there is a value of kx at which this TTM splitting is turning to 0, and so when you pass this point, this TTM splitting can even change the sign.
However, 3 minutes.
However, really interesting thing appears when we go to the second order term, and if we do all the math, you will see that in the Hamiltonian, in the second order, of the perturbation theory, you have the appearance of the term linear in kx, and the expression for this term is given here. So if you look at this term, you will immediately see that this term goes to 0 when the confinement is symmetric along y direction, because either second term, as the first term will turn to 0, but for asymmetric confining potential, this term will be present, and it will give us some additional splitting in circular polarizations. And well, our estimate gives that in realistic structures, it can be about microelectron volts. So very briefly about second part of my talk. The idea here is very simple. So let us consider the two-dimensional exciton, which is placed in the magnetic field plus an electric field. What will be the effect of the magnetic field? If the exciton is moving, then classically the Lorentz force, which is acting on the hole, and Lorentz force, which is acting on the electron, will be directed oppositely. This will mean that the electric dipole moment will appear for the exciton. The expression for this electric dipole moment can be given here. So here is the dependence of this electric dipole moment of the magnetic field. And then if you have the system of the scatterers, which create some electric field, then this dipole moment will interact with the electric field provided by the scatterers. You can write the Hamiltonian in this form, just dipole electric field interaction. And again, if you do all the math, the dependence of the dipole moment on K in this form leads you to the appearance of the effective magnetic field, and the value of this effective magnetic field is given here. So it is proportional to the divergence of electric field, so you need spatial dependence. What will be the effect of this effective magnetic field? We will have, if we do again all the math, and if we calculate the scattering matrix element, we will see that we will have the appearance of the skew scattering term, which will actually mean that scattering of the excitons on the impurities will become asymmetric. And we will have something similar to the appearance of the Hall current. Our estimations using Boltzmann equation give us the value of this Hall current. It can be characterized by Hall angle, and this Hall angle will be something like several %. So here I end my talk, and thank you very much for your attention.
Thank you very much. Thank you very much, Ivan, for this very nice and comprehensive presentation. The paper is open for discussion. We have time for a couple of short questions, please. Maybe I can ask a short one related to the previous part. Then you studied the splitting in the one-dimensional waveguide, yes. Probably even the slide before that. So then you mentioned that the splitting can be non-monotonous
yes.
function.
Yes.
So can you probably explain the physics of the effect a little bit?
Well, the physics of the effect is following. So if we have two-dimensional electron, TATM splitting is fully provided by the presence of non-zero wave vector. Then, if we confine polaritons in the one-dimensional waveguide, then of course along one of the directions, in this case along y direction, the motion will be quantized. So first thing that we will have due to the quantization of this motion will be the appearance of the part of the TATM splitting, which is k independent. So this part is it is just defined by the thickness of the waveguide. But on top of that, still dependence on k survive. Yes, this kx here, it is not disappearing. But if you look on the structure of this Hamiltonian, this kx and ky, they have different phase factor of I, which means that they will enter in the combination kx squared minus ky squared.
Okay, I see. Thank you. There is another question from Guillaume, please.
Yes, it's about this TTM, in fact, what you said at the beginning. So I remember that again, when we were in Clermont, you explained me very long ago already that because of the square, it is not like Rashba, and you cannot make this mapping to a gauge field. Then I'm not completely sure that it is correct to say that it is not spin-orbit coupling, at least. Because, okay, you cannot make the mapping to a gauge field, that's true for TTM alone, but still it's, so maybe it's not spin-orbit interaction, because interaction, okay, should be mediated by some gauge field somehow, but that it is a coupling between spin and orbital degree of freedom, I think it is still okay. Just the mapping part.
Yes, it's of course a matter of terminology. I agree with you that it's legitimate to say that it is some analog of spin-orbit interaction. So the point is that it is not legitimate to say that it is gauge field. So it's not complete analog.
I fully agree with you.
Okay. I do not see other questions at the moment. So let's thank the speaker once again. Thank you very much. And now we turn to the next speaker.